Hey guys, so today we're going to talk about inverse trigonometric functions, which are basically just restricted versions of the graphs that we already know. So just keep in mind that they're always in the form, just for example, we'll go y equals sine negative first x. And it's not the same thing as y equals the cosecant of x, even though you would write this as y equals 1 over the sine of x. So this and this are not equal. And I know that for the test they said don't worry about the graphs, but I'm going to show you how it's actually easier to remember the values of the inverse functions when you know the shape and size of the graphs. So we're going to start with y equals the inverse sine of x. So, like our regular sine graph, it looks like this. Midline high, midline low, and so on. So, and then back this way. So what you would do here is you would take one section of the graph, so go here. Because to actually be a function, the graph has to pass the horizontal line test. So, y equals sine of x actually doesn't pass the horizontal line test, so it's not a function. But this highlighted part here is. And so to make it inverse, you're just going to flip that. So basically you would just do this. So then the inverse sine graph looks like this. And just note how those ends are capped so it doesn't keep going. For sine graphs, the domain will be 1 inclusive, and the range will be negative pi over 2, pi over 2 inclusive. And so if a question asked you, what's the inverse sine of root 2 over 2, you would look at where, where on the graph is the value root 2 over 2. So that's about here. And like we know on our unit circle how the corresponding value is pi over 4. So this would equal pi over 4. And same thing, if a question was sine 1 of negative 1/2, you would look at where the graph reaches negative 1/2, which is like here. Like on the regular unit circle, that would be 11 pi over 6, but it's restricted, so you're just going to go with negative pi over 6, which actually is negative pi over 6, if you think about it. And so cosine graphs will function much the same. So you're just going to take one section of the graph, so we're going to take this part. So therefore, it passes the horizontal line test, and then we're going to flip those values. Now it looked very much the same for sine graphs, but that's not the case for cosine graphs. So this point here is pi over 2, 0, which means that we have to flip those values. So then it'd be 0 pi over 2. So our inverse cosine graph actually looks like this, with domain negative 1 inclusive, and with a range of 0 to pi inclusive. So this is not the same as sine graphs because the range goes all the way to pi. So if somebody were to ask you, well, not somebody because you're not someone, not going to ask you on the street, but if a question said the inverse cosine, and this should be capital, inverse cosine of root 2 over 2. Same thing, it's still going to be pi over 4. But if the question said the inverse cosine, still should be capital, sorry, of negative root 3 over 2, well, that's about, that's about thereabouts. And so you can go all the way to pi, so we know that the furthest negative cosine with a pi restriction is 5 pi over 6. And once again, y equals the inverse tangent of x is much the same, so we're just going to take this part of the graph, and we're going to invert the values. So that graph will actually end up looking like this. So I'm going to keep going. Just with asymptotes like this at... the domain here is negative infinity, positive infinity, and then the range is negative pi over 2, pi over 2. So these are what the asymptotes are. Notice how it does not include negative pi over 2 and pi over 2, so just don't make that mistake. Like the nice values cap at pi over 3. So if you were to ask what's the inverse tangent of root 3, well, think about where root 3 would be in the unit circle. We know that it would be pi over 3. But then if you were asked what is the inverse tangent of negative 1, it would be negative pi over 4, because, usually it would be 3 pi over 4 or 7 pi over 4. But that's not included in the range, so it has to be negative pi over 4. So, like, the range is the same as the sign, except for the pi over 2s are not included. And then there's also graphs for y equals the cotangent, the inverse cotangent of x, y equals the inverse secant of x, and y equals the inverse cosecant of x. I'm just gonna list those quickly here because we're not gonna be tested on that very much, and they're not that complicated. So if you follow the previous rules of the inversing of the graphs, the cotangent graph will end up looking like this. So like the tangent graph but flipped and upwards. And then the range of that function would be 0 radians to pi, but not inclusive. So your 0 radians and your pi are asymptotes. Secant and cosecant graphs are kind of weird because like in the original graphs, they have different sections. So just know that a secant graph will look like this, and then it'll have asymptotes at the x-axis and at y equals pi, and that the cosecant graph, it's getting a little close. Hang on. Okay. That's the cosecant graph will look like this. So asymptotes at y equals pi over 2, and then y equals negative pi over 2. So then the range for a cosecant graph is negative pi over 2. Here, so this is inclusive for cosecant, and then for secant it would be this. And just some minor corrections. Sorry, this should actually be a y because it's the y values. So yeah, you won't have to graph these, but it's helpful to know the shape of the graph in case you forget the restrictions. So yeah. So I'm going to run through a couple of problems that you might encounter while venturing into the dangerous world of inverse trig functions. So we'll just start simple. So cosine, the inverse cosine of 1/2 pi over 3, inverse, so a cotangent of root 3 over 3 is pi over 3. It really helps to know these values, so I would advise studying those. You can memorize those, but the shape of the graphs can also help. The inverse secant of, say, 2 would be pi over 3. There's a lot of pi over 3s. And then the inverse cosecant of -2 would be -π/6, and these are just some examples. And pro tip, so in some questions you might get like a question like, sine of the inverse, sine of, say, I don't know, π/3. Just know that any function times its inverse function of something is always going to be that number. So the sine of the inverse sine of π/3 is just π/3. The cosine of the inverse cosine of π/3 is π/3, and so on. Within the restrictions of that function. And so let's do something a little more complicated. So let's start with the cosine of the inverse, tangent, that's a negative, of 5/12. So let's just say that theta equals the tangent, the inverse tangent of 5/12. So let's put this into like a triangular form. So here, let's put this on the graph. So if this is theta, so we'll have to make this 5/12 because tangent is opposite over adjacent. So then this would be 13. And the question is just basically asking, what's the cosine of theta? And so, theta is adjacent over hypotenuse. So the cosine of theta is just 12/13. And that's your answer. And so let's try another one. So let's do the cotangent. I'm sorry, these should all be capital. I'm just failing at that epically. The inverse sine of -1/3. So let's plot this, and just remember that like for sine graphs, you only get to use this part of the coordinate system. So it would therefore be so if this is theta, it would be 3 and 1. Because that's the only way that you can have a negative coordinate if the sign is negative. So then this part here would be √2/2. This is theta here, and this should be negative. So it's basically just asking, what's the cotangent of theta, and it's the opposite of your tangent. So it would be the adjacent over the opposite. So √2, 2√2 over -1, cotangent of theta equals -2/2. That's your answer. And so those back there were called composite functions, and these are kind of like composite functions. So we just had to break these down. So let's make a triangle for these. This is let's make this angle A for here. And then we'll make this angle B for here. So the cosine of A is just 3/5. So this would be 4. Same thing over here. Sine of B is 5/13. So it would be 5, 13, and then 12. And so just treat this as a regular problem where you would just do, tangent of A plus B, which, as we know, is tangent of A plus the tangent of B over 1 minus the tangent of A tan B. So this is A, this is B. Well, the tangent of A would be 4/3 plus 5/12. 1 minus 4/3 times 5/12. Simplify this, and you get 63/16. So this would be your final answer. And that will be the setup of most of the problems that you'll see like this. So you're going to have to use, like the tangent of a plus b, sine and cosine of a plus and minus b, that sort of thing. So as long as you know those formulas, and as long as you can, as you remember the restrictions on each function, you should be fine. And that is Elephine in the spirit of a certain Spanish teacher.